So the next and last talk of today will be given by Andreu Masó, who is doing the PhD here in the University of Valencia, in our group. He will talk about boson stars in Palatini FOR gravity. Andreu, when you want.
Okay, hello, good afternoon to everyone, or good morning, depending on your reference frame. Thanks for attending, and I'm going to present you the work I am carrying out together with my advisor, Gonzalo Olmo, and in collaboration with Tony Font from the Department of Astronomy and Astrophysics here in Valencia, and Nico Sanchez, who is now in Lisbon. Okay, I will start talking a little bit about boson stars in GR. Two good references I would like to recommend you are the review from Liebling and Palenzuela, and also the work of Herdeiro Pombon Radu about boson stars, Proca, and Dirac stars, which are very illustrative and I have used for this work. In order to introduce what a boson star is, let me talk first about geons, which are the ancestors of boson stars. The term geon comes from the abbreviation gravitational electromagnetic entity and was introduced by John Wheeler in 1955 in order to overcome the concept of body in GR, since usually by body we refer to one-dimensional idealized object. Okay, so he introduced these geons in order to overcome this the concept of body, and they are a standing electromagnetic wave bent into a closed circular toroid of high energy concentration, and it is confined in that region by the gravitational attraction of the mass associated with its own energy field. Although a stationary solution for geons could not be provided satisfactorily, and some years later, in 1968, stationary geons were found in the Einstein-Klein-Gordon system by David Cope, who substituted the electromagnetic field by a complex scalar field. This concept has evolved also with the work of Bonazzola and Ruffini to what nowadays is known as boson stars, even though at the moment we're named like that. Okay, so boson stars are made of a massive oscillating complex scalar field. These oscillations originated an effective pressure via the Heisenberg uncertainty principle that prevents the gravitational collapse, while the mass mu of the field creates an energy lamp that counteracts the dissipative nature of the field. Even though the field is not static, the space-time is static. Okay, so boson stars are composed of many coherent modes with different frequencies. Here I have plotted the curves of existence for fundamental modes. Each point of the curve is a different boson star. As you can see, there is a minimum value for the frequency. This can be explained because only fast enough oscillations will prevent boson stars from the gravitational collapse. In the same way, there is a maximum frequency, in the sense that beyond this point, the boson star will not hold together. This curve is supposed to extend to infinity. However, for numerical reasons, it's only, I could only extend it to this point. Okay, another property of the boson stars is that maximal ADM mass of these objects are inversely related with the mass of the constituent boson. Thus, if we want a stellar mass boson star, ultralight bosons with mass below 10 to minus 19 gigaelectron volts have to be provided. In order to form a massive object, these ultralight bosons have a very large occupation number. So boson stars are basically macroscopic Bose-Einstein condensates. Also, these objects are candidates to shed light to some astrophysical scenarios. For example, they could explain the origin of the recently detected intermediate mass black hole mergers. And an important feature of these objects is the absence of horizons, which could make the innermost regions of those objects accessible to observations, and potentially offering new insights on how to extend Einstein's gravity. In this sense, it is of interest to explore how structural properties could be affected by modifications of the gravitational Lagrangian. We will explore f of r theories, since they offer a large amount of freedom while keeping the field equation within our reasonable limits of simplicity. Moreover, we will use Palatini f of r theories, where the metric and connection are two independent objects. And also because this formulation offers the possibility to map the problem of a modified gravity theory minimally coupled to a scalar field into a standard problem in GR minimally coupled to a modified scalar Lagrangian. By this property, we are able to use standard numerical methods to solve this scenario. Here I wrote down both actions and the action in both frames, which will lead us to represent the same scenario. There exists also a conformal relation between the metrics. So in order to go from one frame to the other, only an algebraic operation has to be done. And okay, so in order to use the mapping, numerically, we have to provide a specific form for the f of r function. We will focus on quadratic theory. So now we can map the material Lagrangian of the scalar field into the GR frame. As we can see, the Lagrangian is now quadratic with the field. And since we are studying spherical symmetric configuration, our metric ansatz in polar areal coordinates will be described in this way, which is the typical way to describe these metrics for boson stars. Okay. So the Einstein field equation will bring us to this, the two first differential equations for the metric parameters alpha and beta. And the equation of motion of the scalar field will provide us with the third one, where we have defined C as the radial differential of the field phi. I'm displaying you this huge equation just to point out that there appears some denominators that can happen to be zero in some points. Okay, so now let's set some boundary conditions in order to solve numerically the equations. We have to set them in the f of r frame. Don't forget, this is the physical one. And then we map the boundary conditions to the GR frame, where we are solving the problem. We impose asymptotic flatness. This is from far enough, the spacetimes look like Schwarzschild spacetime. And we impose also a regularity at origin in order to the function be continuous and smooth at that point. Okay, so what we get is that imposing asymptotic flatness and regularity at origin in the f of r frame implies the same at the gr frame, which is nice. We can see too that the values of the field phi and the metric function alpha are an unknown finite number, which we will get from solving the system. Okay. So these are the solutions. We solve the system of differential equations, and we get this course of stability. Here I have chosen a positive and a negative value for the gravitational coupling parameter chi in order to explore both kinds of theories. Its magnitude is set to 0.1 since it is big enough to notice differences from GR, and what we are doing here is just a qualitative approach. Okay, so let's analyze what the results mean. First of all, the solution obtained indicate that spherically symmetric stationary boson stars are robust under modifications of the gravitational dynamics for a broad range of gravitational coupling chi. For small values of the scalar field, the properties of boson stars are hardly distinguishable from GR. However, for higher values, differences arise. Most notable one is that in GR we could find solutions for an arbitrarily high value of the scalar field, while in f of r, the domain of existence of boson stars is limited from above. Why cannot we find solutions beyond this point? Okay, basically the denominators of the differential equations goes to zero, so these equations diverge, and computers in general doesn't like to work with infinity. If we monitor the conform factor f of r for solutions close to this last point, this end point of the course of existence, we realize that it goes to zero at the origin. This opens the door to the idea of the formation of a wormhole. Let's recall that the conformal relation between metrics. So we have the area of the two spheres in one frame, in the GR frame. It's equal to the conformal factor times the area of the two spheres of the f of r frame. Okay, so what we have is that when x squared goes to zero, the conform factor tends to zero also. Then r squared could be free to have a non-zero minimum. This will mean that the area of the two spheres in the f of r frame shrinks to a minimum and then grows again. This kind of behavior has been studied also for static massless scalar field configurations in some works by Afonso Olmo and Andreu Garcia. However, further work has to be done to be completely sure about what is happening here, and it's a work still in progress. Okay. Time evolutions have been made also. Roughly speaking, what we do is we take one of the static solution we found, and after a coordinate transformation, we evolve these boson stars using the BSSN formalism, Baumgarte, Shapiro, Shibata, Nakamura formalism. In GR, we find the three different fates for the boson stars depending on its mass and its particle number. One is long-term stable, other is unstable and will migrate to a stable solution. And the last one, which is unstable and ends with the dilution of the boson stars. For the FFR stars, we have found the same behavior, three regions with small differences. Here I plotted some examples. This is the static, the stable solution, the unstable solution that migrates to a stable one. Those oscillations are numeric. And the last one, which is the dilution of the boson star. Okay, so futures perspectives in this work. As we are seeing, FFR boson stars have a similar behavior as the ones in GR. In GR, spinning boson stars have a toroidal shape and are unstable. They lose angular momentum and decay to the spherical non-spinning solution. And during that transition, gravitational waves are emitted. If we could form spinning boson stars and time evolve them in FFR, maybe we may see imprints of FFR gravity in the wave form of the gravitational waves emitted. Also, computing boson stars quasi-normal modes will help us to get also these gravitational wave signatures, and are the steps that has to be done in order to do more complicated simulations like head-on collisions or mergers, which could be really nice and interesting to study. And also other works that can be done here is repeat this construction, but now with RBG theories. So that's all. Thank you.
Thank you very much, Andreu. Let's see if there are some questions. We have one question, Caio.
Yes, so thank you very much for the seminar. So can you go back to the mass radius curves that you have for these boson stars? I found
this one.
No, yeah, no, the other one. This is mass and center of the mass radius. The one that you have going up, yeah. This is very interesting. Yeah, the right one is very interesting because I found it to be very similar to the one that people found. So this is just with the mass term, right? You don't have any other self-interactions in your potential for the scalar field.
No, I have done also with self-interactions, but more or less happens the same. No, there's not noticeable differences.
Yeah, this behavior is similar to what people saw in the case of a Proca star, so a boson star with a vector field, but you include self-interaction. So if you include the next order term in the self-interaction, your mass radius relation will do precisely what your green one is doing. It's nice. I mean, I think perhaps you could trace some parallel in your case to the one with the Proca star. Maybe some of the terms are similar. I know that I mean, physically it's a very different scenario, but these similarities are intriguing.
Yeah. Oh, thank you for your comment.
Yeah, and also the direction, it does the same. I mean, if you consider the negative values for the self-interaction, it goes like the red curve, and if you consider positive, it goes like the green curve. It's very intriguing.
Yeah, also here what happens is when I add a negative self interactions, the energy conditions are not accomplished. So sometimes tricky things happens and is not too completely well behaved. And I have like formation of what I suspect are wormholes. Because okay, here also the thing is that what I have here are none of them are solution of wormholes or other compact objects, or because I cannot compute that solutions. I can only compute well-behaved solutions.
Yeah.
So it's complicated to explore beyond the behaviors.
So also the maximum mass configuration, if you increase the value of if your parameter there, do you see can you see a bigger increasing of this maximum mass?
If I change the
Yeah, yeah,
coupling parameter, yeah, it changed the maximum mass, of course, as we can see here in this plot.
yeah. But you, I mean, in the plot, the increasing is just is very small. So that means essentially that your stable boson star, I mean, I imagine that they will not be that different from the GR one.
Exactly,
So
they are not that different because theory is quadratic with the concentration of energy and density.
yeah,
So we need
what I'm
a higher.
yeah, what I'm thinking is how much mass increase you can have in this theory. I mean, if you push the parameter to the limit, that's
I
so you have
think right now it's quite on the limit because
okay.
it's a really high parameter. It's not expected to be as high.
I see, I see, I see. Okay,
Mm.
thank you.
Okay, so there is another question from Adalton. Even and odd modes are separable in such a scenario as well for computing the perturbations?
Sorry, I think I don't understand the question. Can you repeat it?
It's written here if you want to read it. Even and odd modes are separable in such a scenario as well for computing the perturbations?
I don't really know. I don't have an answer for this question since I haven't studied this yet.
I think
Okay.
if I could add something, I think they would be separable. I mean, you don't have any terms that, for instance, if you would add something like the Schoenheim term, maybe you have some mixing, but I think they would be separable as well because of the terms that you are adding in the action. So that should not be a problem.
Okay, thank you.
Okay, and we have another question from Fabrizio.
Yes, can you hear me?
Yeah.
Yeah, well, thank you very much for your nice talk. And I just have one comment that, so at some point you were, when you were showing the existence plot line, yeah, like this one, for example, I think you said something that like in GR, you can choose the central value of phi as large as you want.
Yeah.
I'm not really sure about this. I mean, I never thought about this, but I think even in GR there should be some kind of limit because the solutions, when you increase central phi, they become more stiff and more compact. And I guess
Yeah,
there's,
and can end in a black hole or something like that, no?
yeah, I'm just saying that I think you cannot really increase this parameter as much as you want, even not only for computational reasons, because at some point you will get something that is very stiff. So I don't
Yeah.
think it's really possible. That was
Yeah.
just a comment. I never thought about this, but
No, but you're right, and makes sense what you say, and I have just spoken too easily, but it makes sense.
Yeah, that was just a comment. So, well, but thank you very much. It was a really nice talk.
Okay, so there are no more questions. So thank you, Andreu, for your talk.
Thank you.